In this video, we're going to do a comparison by proving the same theorem using both types of indirect proof. So we're going to prove something using a proof by contradiction, and then we're going to prove the same thing using a proof by contraposition. So you can kind of see how they're similar and how they're different. So first, recall the way we do a proof by contradiction. Proof by contradiction, we want to start by assuming what we're trying to prove true is false. So we're trying to prove some universal conditional statement. Is true. Right? This is our goal. So what we want to do is suppose the negation. Now, if you recall, the way we write that negation is we're going to, the for all becomes that there exists, and we have P of x stays the same, and the negation of Q of x. So the negation of for all x, P of x implies Q of x, is there exists an x such that P of x and not Q of x. And then we want to derive a contradiction. So we want to show that supposing there exists an x such that P of x and not Q of x causes a contradiction. Right? And if the negation cannot be true, then we can conclude that the statement is true. To do a proof by contraposition, we're first going to, as always, express the statement as a universal conditional statement. So this is what we're trying to prove true, that for all x in some domain D, that P of x implies Q of x. And to do this with a proof by contraposition, we're going to take the contrapositive. So the contrapositive of this is for all x in D, the negation of Q of x implies the negation of P of x. Right? And as we know, the contrapositive is equivalent to the original statement. So we're then going to do a direct proof using the contrapositive. So recall, we do a direct proof by supposing this first part and concluding the second part. So we are going to suppose x is any element in D such that Q of x is false. And we're going to show that that means that P of x is false. So if you're comfortable with the direct proof, a proof by contraposition is pretty straightforward. All we do is we take the contraposition of the statement and then do a direct proof. Okay, so now we're going to prove the same theorem true using both a proof by contradiction and then next a proof by contraposition. So this is a little bit of a complex theorem. This is our theorem. We're saying if the sum of two numbers is even, let's call that P, then both numbers are even or they are odd. We'll call that Q. Now this is a tricky problem because there's a couple ways of doing it. You may notice that there's an or right here. And we want to be careful with that or, because you want to think big picture. Both numbers are either even or they are odd. What does that mean? Well, it means they have the same parity. Parity is the term that describes if a number is even or odd. The parity is either even or it's odd. So let's start by formally writing this out a little bit more mathematically, and then we'll take the negation and we'll see what that gives us. So another way of writing this is to say, we're talking about any two numbers, right? We don't exclude it here in P. So I'm going to rewrite this as for all m and n in the integers. And I could pick any two variables here. I could have x and y. I could do a and b. It doesn't matter. They're just variables. I'm going to say if m plus n is even, now here I have a choice. I could stick with the or as is written in the Q up here at the top. Or I can change this and I'm going to rewrite it as then they have the same parity. Get that centered there. Make sure I'm spelling that right. Yep. Okay, and writing it this way is going to make taking the negation easier. Because recall, we're doing a proof by contradiction here. We're doing a proof by contradiction. So we need to start by supposing the opposite. So we're going to suppose... well, first let's calculate the opposite of this. So the opposite of this, we want to suppose the negation, which is equivalent to saying that we suppose that there exists an m and n in the integers such that, remember, we leave P alone. M plus N is even. And now I want to take the negation of Q. We've written Q in two different ways. These are both Q. So taking the negation of the way we wrote it here is going to be easier because there's no ands or ors. It's a statement. It's a simple statement. It's not a compound statement. Let's see what happens if we do the negation of that. So, and they have different parity. Now, is that the same thing as taking the negation of this top Q? Right up there. Well, think about this for a moment. If both numbers are either even or they are odd, the opposite is that we have one of each. Right? In other words, different parity. It's easy to get hung up on this or. Whoa. And you can do it if you use the or, you'll still get to here, but it's a few more steps. You'll get the same thing. It's the same thing. These aren't different. But you will have a few more steps. Okay. At the end of this video, you'll see I have a typed up version where I do it the other way. Okay. So if I have, we're going to suppose that there exists an m and n in the integers such that m plus n is even and they have different parity. So what I can say is I can say without loss of generality, which is sort of just a way of saying it doesn't matter which way I say this, so I'm going to pick a way of saying it. We're going to let m be even and n be odd. And I can say that without loss of generality because these are just variables. So I know I have one even number and one odd number, and I'm just giving them names. It could be the other way around. I could say it however I want. I'm not losing this generalness that we take advantage of when writing proofs. Okay. So what do we want to show? We want to show that this leads to a contradiction. Okay. So since m is even and n is odd, we know that m is equal to 2 times some integer k, and n is equal to 2 times, now remember I can't use the same variable k, otherwise I'm implying that these are consecutive integers. So I'm going to pick a different value, q plus 1, because n is odd, for some k and q in the integers. Now I'm running out of space, so let's go to the next page. But notice what we're going to do next is we're going to try to figure out what does m plus n, what is m plus n? And our theorem says that it's even, and we want to show a contradiction, so we're probably going to show that with these m and n, it's going to cause m plus n to be odd, and that will be our contradiction. Let's see what happens. So m plus n is going to equal 2k plus 2q plus 1 by substitution. And I can write that as 2k. I can actually save some space. I can do that as I can just write that as plus 2q plus 1 because there's no negative sign to distribute. And I can factor a 2 out like that. This is by factoring out a 2. And I'm going to notice that this looks a lot like the definition of odd. All right, I'm not there yet, though. I can't say that that's odd. That would be jumping to a conclusion. So I first need to say, let r, or some variable, equal k plus q. We're going to notice that r is an integer. Why can I say that? Because of integer closure. And that's really important because with that, I can conclude, so m plus n equals 2r plus 1 where r is an integer, which is the definition of odd. Right? But if you recall, looking back to the previous page, we said that it was even. Right here on this second line, we said we're going to suppose that m plus n is even. And we found that it's odd. There's our contradiction. You always need to note the contradiction. Therefore, the negation is false, and our original statement is true. And that original statement was this theorem up here. Okay, so we just proved this theorem by contradiction. Now we're going to prove it by contraposition. So to solve this problem by contraposition, we're going to start with the same more formally written out statement that we had before. So I just copied that one and put it here. And now what we're going to do is we want to write its contraposition. So if you recall, the contraposition is going to be not Q implies not P. So let's write that here. So we're going to say this is equivalent to, for all m and n in the integers, if m and n do not have the same parity, then I'm going to take the negation of P. M plus N is odd. Okay, so we now want to start by supposing this first part of the contrapositive. Okay, so we're going to say, suppose. Now what's another way of writing that? M and n are any integers that do not have the same parity. I guess that's as well as we can do. Without loss of generality, let m be even and n be odd. Okay. Same reasoning as before. What do we want to show? Well, we want to show the second part, that m plus n is odd. We want to show so that's our goal. So as with the previous one, we're going to say so m equals 2k and n equals 2q plus 1 for some k and q in the integers. And now what we're going to do is we're going to use this now to prove our goal, which is that m plus n is odd. Now, this should be ringing some bells with you, because this is really exactly what we did before, right? We supposed that m was equal to 2k, this is right here, down here in the corner, that m was equal to 2k and n was equal to 2q plus 1, and we showed that the sum was odd, which in this case led to a contradiction, because we were trying to show that it was even, right? But for proof by contraposition, we're going to start with m and k being the same exact things, but now our goal is to show that it's odd. And we already know we can do that. We did it before. So let's do it. M plus n is going to be 2k plus 2q plus 1. And again, I don't need parentheses because I don't need to distribute anything. It's by substitution. Parentheses aren't bad at all. I just don't have a lot of space on this, so I'm not using them. And then once again, we can factor. And then we can assign a variable. Let r equal k. Ooh, I factored wrong, didn't I? This should be k plus q. I factored a 2 out. So let r equal k plus q. Once again, we notice that r is an integer due to integer closure properties. So m plus n is equal to 2r plus 1, where r is an integer, which is odd by definition. Now this page should be looking pretty much identical to what we did here. I really could have just copied this first part and pasted it on the other screen. But now it changes. Because in this proof by contraposition, showing that it's odd was our goal, right? This is our goal down here. It's to show that it was odd. So we've accomplished that, which was to be shown. So it's interesting to see how we can take the same theorem and prove it in two different ways. And in a lot of ways, the steps are the same, right? This whole section was identical for both. It was what we were assuming and what we were trying to show that's different. There you have it.